Okay. I'm not, as you can tell, I'm not going to be able to project my voice today, but I think I can at least talk through some of this and hopefully shed some more light on the idea of instantaneous change. This is not a curve that we're looking at in class per se, but it's going to provide a basis for an example of what we're talking about in terms of instantaneous uh, velocity, instantaneous rate of change, right? So you know that the slope of a line, right? When we talk about slope, m for slope. When we talk about slope, that represents the rate of change. Okay, but if you think back to all of the work that you've done with slope in the past, when you talk about rise over run, change in y over change in x, all of those things, you always had 2 points. So when you had 2 points, you could find the slope of a line. In calculus, what you start to investigate is the slope of a tangent line, where you only know 1 point. So finding the slope of a tangent line is finding the rate of change at an exact moment, not between 2 points, but at 1 point. Okay. And we're going to talk about methods for doing that. But the concept itself, right, can be thought of like this. And I've got some slides queued up here that I can kind of walk you through. Okay. Um, Here we have a second point on this curve. And if I connect those 2 points with this green line, we talked about this yesterday, this is called a secant line. Okay. And I could measure the slope of this line using rise over run very easily. But one thing I want to note here is that the distance between these 2 points horizontally right now, for reasons that I'm not going to get into right now, I'm going to call this H. Okay. But if you look at this difference right now, those 2 points in terms of their horizontal distance, in terms of their run, are 3 units apart. And when you look at that green line, it's not relatively close to this black line, the line that I want to know the slope for. But I could find the slope of this line, and that could be an accurate, maybe not an accurate, but a decent estimate for the slope of this line, right? How can we be more accurate? Choose a point that's closer. Now, when you look at the horizontal distance between these 2 points, okay, we have a green line that's here. And when you compare that green line to that green line, which one is a better estimate, right? The second one. Why? Because the distance here shrunk. We made it smaller. What would be an even better estimate? How about if I picked a point that was even closer? So now the distance here, right, has shrunk even more. So every time we shrink that change in X, let's call it, every time we make that smaller and smaller and smaller, we get a more accurate representation. Now look at that green line, very close to that black line. Okay. And we could go through this process over and over and over again, right? I could pick a point that's here and it would be even better. I could pick a point that's here and it'd be even better. The best estimate, and this is where we get into some of the nitty gritty of calculus, let's say, the best estimate would be if that difference was zero. It's impossible to do that because when you talk about, the change in y over the change in x, or you talk about the rise over run for the slope of this line, we can't let that be zero because we'd be dividing by zero. Okay. So what we do is we give our best estimate by keep shrinking that over and over and over again. We're going to learn a method coming up now, maybe tomorrow or in the next couple of days, called limits, which allows us a way to do that.